Hi, grade 10s. So today we are going to learn about acceleration, and it will connect to our understanding of velocity and speed and distance and displacement and the relationship between all of these things together. So far we've actually only been discussing uniform motion, which means we've been talking about velocity. We haven't talked about if you accelerate or decelerate. So if you look at these two graphs, okay, this one is increasing velocity and this one is decreasing velocity. Velocity would be our example of driving on cruise control on the highway. You're driving 50 kilometers an hour. You are not accelerating or decelerating. Okay. So if you were to think about riding in an elevator, at what part in the elevator ride do you feel the motion? Usually it's right at the beginning. You feel that acceleration, or when the velocity is changing. When it's actually just moving at a constant velocity, not accelerating, not decelerating, you don't feel the motion. Okay? Even think about when you're on an airplane. You're experiencing quite extreme speed of around 300 kilometers per hour, but you can't feel anything. It feels like you're kind of just sitting there. But you do feel the acceleration when you take off or when you land. So if an object changes velocity, so speeds up or slows down, the rate of velocity change is called acceleration or negative acceleration. And we do prefer to use acceleration in the negative. Okay, so that is an important piece to note. So formula, how are we going to use this? This guy will be found on your formula sheet. Whoa, I'm all over the place today. And what it is A with that vector symbol over top of it. I lost it here. That stands for acceleration. Your units for acceleration is meters per second, and it has to be squared. There is a difference between the units of velocity and acceleration. V, or delta V, stands for change in velocity. So you can have a starting velocity and a final velocity. And then we have our delta T, which means change in time, which is going to be in seconds. All right, so acceleration can be in the same direction as velocity. It's usually positive, or it can be in the opposite direction of velocity, which means then it would be negative. So a car speeding up has positive acceleration as velocity is going up, but a car braking has negative acceleration as the velocity is going down. So if you were to look at a position time graph of what this would actually look like, okay, with position on your left-hand side, time on the bottom, as you increase your time or your object, it is increasing its position at an exponential rate, which you're seeing this curve. Velocity time graph, your velocity is increasing at a constant rate, and so you're actually getting a nice slope. Negative acceleration, okay, would look like, a quick two graphs here. So if I was to label these, this is a position time graph. Your negative acceleration would actually curve down, and your velocity time graph would have a constant straight diagonal line downwards. So this would be a VT graph because your velocity is slowing down and your position is also decreasing, but at an exponential rate. So example one, if you were to look at a ball, okay, rolling. And this is kind of what you saw on your Graphs and Tracks challenge assignment. So if your D is 0 meters, so at time at 0, your distance is at 0 meters. So what is the average? The question is average velocity in 3 seconds. Well, we know our formula for velocity is v over dt. This is from our velocity speed lesson. Okay, so in 3 seconds, here's my time in 3 seconds right there. Woo. So the distance would be positive 9 meters. The time is 3 seconds. And 9 divided by 3 is positive 3 meters per second. Now, by me including that positive sign is helping me show direction, and acceleration or velocity is a vector. So that is my positive forward motion. The average velocity between 2 seconds and 3 seconds. So this is when, I'm going to actually put this down below just so I have enough room. V is equal to delta D over delta T. So this is sometimes easier to show our work all in one step. So if I'm going from 2 seconds to 3 seconds, so this is my starting point, and this is my final point. So in physics, we often use D1 or D2. So our second point versus our first point, so I'm going to go D2 minus D1, and then I can take my time of my second one and the time of my first one. So my distance for my D2 is 9 meters. My distance for my other point is 4 meters right there. And my time is 3 seconds minus 2 seconds. So 9 minus 4 is 5. And my time is 1 second. So my answer is positive 5 meters per second. All right. Just going to erase this so I have enough room. So what is the acceleration? So this is the new part of the whole movement. So I'm going to write my formula. Acceleration is a vector, so it needs that vector arrow on top. And delta V, velocity over time. So what is my velocity change over time? So I have my final velocity and my starting velocity. So V2 minus V1. My change in time, T2 minus T1. So 6 meters per second minus 0 divided by, 3 seconds minus 0 seconds. So 6 divided by 3. And I should get 2 meters per second squared. And it is a forward motion. The ball is rolling forward, so I get positive 2 meters per second squared. So that's acceleration. Okay. Example 2. An Aston Martin vehicle, so it's a really fast car, takes only 5.10 seconds to go from a stop to 26.6 meters per second. What is the acceleration? Okay, so that's my question. If we assume the forward velocity to be positive. So this vector addition is just to kind of get you thinking. So this is where the car is. This is my initial place. It stopped. It's now going 26.8 meters per second forward. Okay, so this is my start, this is my end. So I'm going to look for acceleration. So A is equal to V divided by T. V2 minus V1 divided by T2 minus T1. In this case, we're stop to start and it only takes 5.10 seconds. So I only have I don't have two different times. So I'm just going to look at the time overall. So I go from 26.8 meters per second. My original was 0 meters. It's not moving. Divided by 5.10 seconds. And I should get, okay, positive 5.2549. That number keeps kind of going crazy. So we think about our sig digs and we should get, my answer is actually down below, positive 5.25 meters per second squared. If this lets me finish a nice, nope, it's not going to let me do a nice box. All right. So this is acceleration. Example 3. A soccer ball is rolling towards a goalie. So let's say this is the goalie here. Even if it doesn't ask you to draw a vector diagram, it kind of helps you imagine what's happening. So this ball is rolling towards the goalie with a speed of 2 meters per second. The goalie runs up to the ball, kicks it down the field with a velocity. So kicks it down the velocity with the field, down the velocity, down the field with a velocity of 8.6 meters per second. So overall, we know right here, okay, that my number isn't going to be overly great. It also says if the ball only makes contact with the goalie's foot for 0.2 seconds, so this is time, then what is the average acceleration of the ball? Let the movement of the ball towards the goal be positive. So this is positive 2, and this is negative. So A is equal to delta V over delta T. So change in, so V2 minus V1, my time, all right. So V2, this is my second guy, negative 8.6 meters per second, minus positive 2.0 meters per second. So this is where you'll notice the signs become really important. Otherwise, your answers will actually be incorrect. Your delta time is 0.62 seconds. So if I was to do the subtraction, I should get, okay, negative 10.6 meters per second divided by 0.62, and A is equal to negative 1.709677 meters per second squared. So sig digs, I only get 2. So I'm going with 1, 2, negative 1.7 meters per second squared. Okay, example 4, last one. A car turns onto a highway. If the car accelerates, so this is where it's actually A is 11.90 kilometers per hour squared from a stop position, how long does it take to reach 100 kilometers per hour? So this one's really good to pull your information out. if you're kind of confused. So A is equal to 11.90 kilometers per hour squared. It says from a stop position, so V1 is 0 kilometers per hour. It's not moving. V2, you want it to be at 100 kilometers per hour. And it's asking you how much time does it take. Okay, so formula. So delta V over, forgot the delta, over delta T. This one, I like to rearrange right off the bat. So I'm looking for delta T, which means I need my T on top. So I have to move it to my other side. So I'm going to multiply by T. Okay, so T times A is equal to V. And if I'm looking to solve for T, I'm going to divide each side by A. So this is another one. If you don't love algebra, write this formula down. You're going to want access to it. Okay, so V2 minus V1 divided by A. So V2 is 100 kilometers per hour minus 0 kilometers per hour divided by 11.90 kilometers per hour squared. So we do a little math, subtract, basically 100 minus divided by 11.90 should give you 8.403361345, but with rounding and sig digs, I get 3. So 8.40, and because we're dealing with kilometers per hour, my unit for time in this situation is hours. Time does not have a direction because it's a scalar, so we don't have to put a direction on it. Okay, that is it, guys, for acceleration. So if you have any questions, ask away. And this is kind of the end connection of velocity, distance, and acceleration all together. We'll move on to energy next. Bye.